In this video, we're overclocking the Intel Core i9-12900K up to 5.5 GHz using EK Quantum water cooling and the GIGABYTE Z690 AORUS Master motherboard. Alright, there's a lot to cover, so let's jump straight into the video. The Intel Core i9-12900K is part of Intel's 12th generation core processor lineup. Intel Alder Lake has an all-new core design with performance hybrid architecture featuring performance cores and efficient cores. It is built on the Intel 7 process technology, formerly known as 10nm enhanced superfin. It's a scalable SoC architecture, which means Alder Lake will cover all client segments from 9W for ultra-thin notebooks to 125W for gaming and workstation desktops. Well, 125W plus. The overclockable K-SKU processors again come in three flavors: Core i9, Core i7, and Core i5. Each of the three flavors has a K and KF variant. The only difference between the two variants is that the KF comes without integrated graphics. The Core i9-12900K processor has 8 P-cores and 8 E-cores with a total of 24 threads. The base frequency is 3.2 GHz for the P-cores and 2.4 GHz for the E-cores. The maximum single core boost frequency is 5.1 GHz for the P-cores and 3.9 GHz for the E-cores. The maximum all-core boost frequency is 4.9 GHz for the P-cores and 3.7 GHz for the E-cores. The favored P-cores can boost 100 MHz higher to 5.2 GHz. The processor base power is 125 watt and the maximum turbo power is 241 watt. A major change from previous architectures is that Alder Lake is moving away from the TDP concept and instead has two power-related specifications: processor base power, formerly the TDP and PL1, and the maximum turbo power, formerly PL2. This is sort of in line with how the processor frequency has a base frequency and a maximum turbo frequency. Another major difference between Alder Lake and really any other Intel Core processor is that, at least for the K-SKU CPUs, PL1 is by default equal to PL2. That effectively means that Intel has enabled near unlimited peak turbo by default. In this video, we will be covering three overclocking strategies, starting out from the easiest one going to the most complicated one. First, we increase the performance headroom by unlocking the Turbo Boost 2.0 limits and enabling XMP 3.0. Second, we test out three OC profiles available in the Z690 AORUS Master BIOS. Lastly, we do manual overclocking to get the most performance out of our system. However, before we jump into the benchmarks, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. Along with the Intel Core i9-12900K processor and GIGABYTE Z690 AORUS Master motherboard, in this guide we will be using a pair of 16GB AORUS RGB DDR5-6200 memory sticks, an RTX 2080 Ti graphics card, a 512GB AORUS RGB M.2 NVMe SSD, a Seasonic Prime 850W Platinum power supply, the Elmo Labs Easy Fan controller, and EK Quantum water cooling. All this is mounted on top of our favorite open bench table. The cost of the components should be around $4,279. I covered the Elmo Labs EFC in a different video on this channel. Without going into too many details, I have attached an external temperature sensor from the water in the loop to the EFC. Then I used the low-high setting to map the fan curve from 25 to 40 degrees water temperature. This is used for all overclocking strategies. We used Windows 11 and the following benchmark applications to measure performance and ensure system stability. Prime 95 doesn't quite work out of the box with the Alder Lake CPUs due to its complicated configuration, with the P-cores having hyperthreading and the E-cores not. However, you can still set up Prime 95 so that it runs on all cores at the same time. You just have to adjust the local.txt text file settings. For the Core i9-12900K, set num CPUs equal 24, that's the total amount of logical processors, and set num hyperthreads to 1, meaning every logical processor will run one thread. Before we do any overclocking, we first have to check the system performance at default settings. Please note that the GIGABYTE Z690 AORUS Master by default unleashes the Turbo Boost 2.0 power limits. So in order for you to have an idea what are the default settings, you have to first go into the BIOS and enter the advanced mode and stay in the tweaker menu, enter the advanced CPU settings submenu, set turbo power limits to enabled, set package power limit 1 TDP watts to 241, set package power limit 2 watts to 241, set package power limit to time to 56. Then save and exit the BIOS. Here's the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4700 MHz and the average CPU E-core clock is 3700 MHz with 1.128 volts. The average CPU temperature is 84 degrees Celsius and the average CPU package power is 241 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4892 MHz and average CPU E-core clock is 3700 MHz with 1.186 volts. The average CPU temperature is 83 degrees Celsius and the average CPU package power is 240 watts. Now let us try our first overclocking strategy. One more thing before we really get started. Locate the CMOS clear button. Pressing the CMOS clear button will reset all your BIOS settings to default. This is useful in case your system does not boot up after overclocking or if you want to start your BIOS configuration from scratch. The CMOS clear button is located on the rear I/O panel. In our first overclocking strategy, we simply try to benefit from unleashing Turbo Boost 2.0 power limits and by using XMP 3.0. Intel Turbo Boost 2.0 technology allows the processor to run its cores faster than the base frequency if there is sufficient current, power, and thermal headroom. The obvious advantage is opportunistic performance improvements in single-threaded and multi-threaded workloads. The Turbo Boost algorithm works according to a proprietary EWMA formula. This stands for exponentially weighted moving average. There are 3 parameters to consider: PL1, PL2, and tau. Power limit 1, or PL1, is a threshold that the average power will not exceed. Historically, this has always been set equal to Intel's advertised TDP. Very importantly, PL1 should not be set higher than the thermal solution cooling limits. Power limit 2, or PL2, is the maximum power the processor is allowed to use for a limited amount of time. Tau, in seconds, is the time window for calculating the average power consumption. If the average power consumed is higher than PL1, the CPU will reduce the CPU frequency. Obviously, Turbo Boost 2.0 is present on Alder Lake, as it is the main driver of performance over base specification. A major difference between Alder Lake and really any other Intel Core processor is that, at least for the K-SKU CPUs, PL1 is by default equal to PL2. This is very different from before, where PL1 would equal the TDP and PL2 would range from 200 to 250 watts. This change effectively means that Intel has enabled near unlimited peak turbo by default. For the 12900K, the maximum power limit is set at 241 watts. The maximum performance is therefore entirely limited by the capabilities of your cooling solution. If your cooling solution is insufficient, then the processor will reduce the operating frequency at the maximum allowed temperature, or TJ max. For Alder Lake CPUs, that's at 100 degrees Celsius. Note that the GIGABYTE Z690 AORUS Master has, by default, Turbo Boost 2.0 power limits unleashed. So, no need to make any BIOS changes to benefit from the additional performance. Intel Extreme Memory Profile 3.0 is the new XMP standard for DDR5. It is still largely based on XMP 2.0 specification, but it has a couple of additional features. The XMP 3.0 standard is designed with 6 sections. One global section describes the generic data, which is used across all the profiles. The other 5 sections are designed for 5 profiles respectively. Profile 1 is meant for the performance profile. This is the standard XMP as we know it. Profile 2 is designed for the extreme settings. This could be higher frequency at higher voltage. Profile 3 is designed for the fastest settings. This could be tighter timings at higher voltage. Profiles 4 and 5 are rewritable and meant for user custom settings. There's a lot more to the new XMP 3.0 standard, which is outside of the scope of this overclocking guide. By the time this video goes out, I should already have a more detailed overview up on my channel. GIGABYTE has put in quite a bit of effort to support all of the new features that come with the new XMP standard. Let's have a quick overview. First, in easy mode, you can select the different XMP profiles with the click of a button. So, no need to access the advanced options to benefit from XMP. In the advanced mode, there's more options. DDR5 Auto Booster will increase the memory frequency from DDR5 4800 to DDR5 5000. DDR5 XMP Booster lists pre-configured memory profiles for a variety of DDR5 ICs. In my BIOS version, I only get Micron and Hynix, but I expect more profiles for other ICs in future BIOS releases. Extreme Memory Profile gives you access to XMP profiles on your memory module. As mentioned before, XMP 3.0 offers 3 vendor profiles and 2 user profiles. In this case, only the 3 vendor profiles show because I have not made any custom profile myself. In the Advanced Memory Settings submenu, you will find even more options. SPD Info provides you with the SPD information of each of your memory modules. SPD Setup is an experimental feature that allows you to create custom XMP profiles. Entering the SPD Setup submenu opens up a world of memory tuning options. By far my favorite feature is the Performance Index. The index provides you with a quick overview of which XMP profile will give you the most performance. As you can see, while XMP2 gives us the highest frequency at DDR5-6400, XMP1 and 3 should give us better performance at DDR5-6200. I don't know the way the performance index is calculated or am able to gauge its accuracy, but it's a good starting point nonetheless. Then we also see the 2 XMP 3.0 user profiles. These fields are entirely programmable by the user. In the selection menu below the profile columns, we can find a couple of easy options to set the user profile. Clear will clear the custom profile. Current will load the DRAM settings currently set in the BIOS. JDEC will load the JDEC DDR4 4800 settings. XMP1, XMP2, XMP3 will load the settings from the respective XMP profiles. Micron 1234 and Hynix 1234 will load the pre-configured memory profiles from the DDR5 XMP Boost menu we saw earlier. Of course, we can also manually change the values. Clicking Set will flash the SPD with our profile. We will now be able to select it upon reboot. By selecting the user profiles, they will also show up in the Performance Index chart. This will help us evaluate how well our new profiles are scoring against the vendor-provided XMP profiles. As I mentioned, we will be able to select the custom user profiles upon reboot. However, we must make sure to set memory boot mode to disable fast boot. Let's reboot. As you can see, we can find 5 profiles in the Extreme Memory Profile option. Selecting Profile 5 provides us with the DDR5-6600 profile we customized before. Anyway, let's get back to our overclocking strategy. Upon entering the BIOS, in Easy Mode, change XMP Disable to XMP Profile 1, then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. As expected, we see the largest performance difference in multi-threaded applications which were previously constrained by the maximum power of 241 watt. We see up to 7.54% performance increase in the AI benchmark. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4881 MHz and average CPU E-core clock is 3700 MHz with 1.203 volts. The average CPU temperature is 99 degrees Celsius and the average CPU package power is 302.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4900 MHz and average CPU E-core clock is 3700 MHz with 1.189 volts. The average CPU temperature is 84 degrees Celsius and the average CPU package power is 242.7 watts. In our second overclocking strategy, we try to make use of the 3 performance tuning profiles that are available in the GIGABYTE Z690 AORUS Master BIOS. 2 of those profiles you can find under the CPU upgrade option. That's the gaming profile and the max performance profile. The third one is available as its own option, and it's called Enhanced Multi-Core Performance. Each profile has a different approach to performance tuning. Enhanced Multi-Core Performance sets all cores to the maximum available turbo ratio. On the 12900K, that means every core will run at 5.2 GHz. In addition, all E-cores run at their maximum turbo boost of 3.9 GHz. Gaming Profile retains the detailed turbo boost behavior, but disables the E-cores. So the CPU goes from 16 cores with 24 threads to 8 cores with 16 threads. Max Performance Profile set the P cores to 5 GHz and the E cores to 3.9 GHz. It is important to note that only the Enhanced Multi-Core Performance Profile is in fact overclocking your CPU. That's because it runs 6 out of the 8 P cores higher than specification. The 2 other profiles are not actually overclocking, as they run all cores within voltage and frequency specification. For each of the 3 sub-strategies, we'll also be using one of the 3 available XMP profiles. The profiles are XMP1 DDR5-6200 40-40-40-80 at 1.35 volt, XMP2 DDR5-6400 42-42-42-84 at 1.45 volt, XMP3 DDR5-6200 38-38-38-76 at 1.50 volt. For strategy 2A, we use the Enhanced Multi-Core Performance Profile and the first XMP profile. Upon entering the BIOS, in Easy Mode, change XMP Disabled to XMP Profile 1. Enter the Advanced mode and stay in the Tweaker menu. Set Enhanced Multi-Core Performance to Enabled. Then save and exit the BIOS. We reran the benchmarks and check the performance increase compared to the default operation. We see performance gains across the board, but most noticeably in the multi-threaded benchmark applications. That's of course because the default all-core turbo frequency is 4.9 GHz, and this profile increases this to 5.2 GHz. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4856 MHz, and average CPU E-core clock is 3900 MHz with 1.201 volts. The average CPU temperature is 99 degrees Celsius, and the average CPU package power is 303.7 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5099 MHz, and average CPU E-core clock is 3900 MHz with 1.278 volts. The average CPU temperature is 100 degrees Celsius, and the average CPU package power is 304.3 watts. For strategy 2B, we use the gaming profile and the second XMP profile. Upon entering the BIOS, in Easy Mode, change XMP Disabled to XMP Profile 2. Enter Advanced mode and stay in the Tweaker menu. Set CPU Upgrade to Gaming Profile. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. The performance is a mixed bag with the gaming profile. As expected, we see the largest performance losses in multi-threaded benchmark applications, but not all of our results are that straightforward. In CPU-Z single, we lose more than 10% performance despite running the same P-core frequency as default settings. AI benchmark performance in fact increased by about 4%, despite it being a multi-threaded benchmark application. It is fairly memory sensitive, so I think the XMP profile helped here versus stock. CSGO performance increased by almost 6% or 30 frames per second. I didn't look too deeply into why the benchmark results are like this. I'm sure there will be plenty of media out there that will have done a thorough analysis of Alder Lake performance with and without E-cores enabled. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4900 MHz with 1.128 volts. The average CPU temperature is 83 degrees Celsius, and the average CPU package power is 210.9 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4900 MHz with 1.153 volts. The average CPU temperature is 75 degrees Celsius, and the average CPU package power is 176.2 watts. For strategy 2C, we use the maximum performance profile and the third XMP profile. Upon entering the BIOS, in easy mode, change XMP disabled to XMP profile 3. Enter advanced mode and stay in the tweaker menu. Set CPU upgrade to max performance profile. Then save and exit the BIOS. We reran the benchmarks and check the performance increase compared to the default operation. The performance result is again a mixed bag. We lose slightly in single-threaded benchmark applications as all cores are running at 5.0 GHz. At default settings, one core can boost to 5.2 GHz and another core will run at 5.1 GHz. In multi-threaded benchmark applications, we see a performance improvement over stock, thanks to the 100 MHz extra frequency on the P cores, as we increase the all-core frequency from 4.9 GHz to 5 GHz. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4884 MHz, and average CPU E-core clock is 3900 MHz with 1.204 volts. The average CPU temperature is 99 degrees Celsius, and the average CPU package power is 305.5 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5000 MHz, and average CPU E-core clock is 3900 MHz with 1.225 volts. The average CPU temperature is 89 degrees Celsius, and the average CPU package power is 266.6 watts. In our third and final overclocking strategy, we will pursue a manual overclock. We will be using a range of Alder Lake overclocking features, including active turbo ratio, AVX2 negative ratio offset, and advanced voltage offset. Generally speaking, on Intel platforms, there are two ways to manually set the CPU ratio: sync all cores or by the active turbo ratio. Sync all cores basically sets one ratio for all the cores. This is very much the traditional way of overclocking. Of course, back in the day when we only had one or two cores, the quality difference between the cores was relatively small. So there was not that much benefit to max out each core independently. Nowadays, even mainstream CPUs have up to 16 cores. That means the quality difference between the cores can vary greatly. In addition, the heat produced by 16 cores at full load will be much higher than the heat produced by just a couple of cores at a light load. So if you tune your system for the worst case scenario, you will miss out on a lot of performance in the most common scenarios. Active turbo ratio configuration allows us to configure the overclock for different scenarios ranging from one active core to all active cores. This enables us to run some cores significantly faster than others when the conditions are right. On Alder Lake, we can configure the active turbo ratio for P cores and E cores separately. So we can set the maximum ratio for one active P core to 8 active P cores, and for one active E core to 8 active E cores. Note that active turbo ratio configuration is not the same as configuring each core specifically. When using active turbo ratio, we determine an overclock according to the quantity of active cores. For example, if a workload is using 4 cores, then the CPU will determine by itself which cores should execute this workload and will apply our configured frequency to those cores. Intel first introduced the AVX negative ratio offset on Broadwell E processors. Successive generations of Intel Core processors inherited this feature and eventually also added the AVX512 negative offset to it. AVX negative ratio offsets are very useful to achieve the maximum performance for both SSD and AVX workloads. Generally speaking, an offset or 2 or 3 is recommended, but it is highly dependent on not only your cooling solution, but also the motherboard you're using. That is because AVX workloads are very demanding and therefore require great cooling and power delivery. While the function has carried over from Rocket Lake to Alder Lake in principle, there are some big differences in the implementation of AVX ratio offset. First, on Alder Lake, the AVX2 negative ratio offset is only applied to the P cores. The E core frequency is unaffected. Second, by default, the maximum ratio during an AVX workload is the Turbo Boost 2.0 ratio. If you want an offset of 0, so the AVX workload won't trigger a frequency reduction, you'll need to manually set 0. Note that on some BIOSes, programming 0 means programming default, in which case you'll be limited to maximum 51x for the AVX ratio on the 12900K. Just like on Rocket Lake, the AVX negative offset is referenced against each individual core. Prior to Rocket Lake, the AVX offset would be referenced against the all-core maximum ratio. As the AVX offset will be applied to each core separately, you'll have to be a little bit careful when your overclock has different ratios for different cores. Third, Intel has made some changes to how it flags an AVX workload. The effect is that some light AVX workloads will no longer trigger the AVX offset. We can demonstrate this new behavior using Y-Cruncher. We ran the Y-Cruncher component stress tester to run a variety of AVX workloads on the 12900K. We configure the 12900K as follows: 5 GHz for the P cores, 3.9 GHz for the E cores, and an AVX offset of 5 pins. Then we use hardware info to monitor the effective clock during the benchmark. During the Y-Cruncher workloads, we see that during the BKT, the P-core effective clock frequency is 5 GHz. Since this is a non-AVX workload, it's as expected. Then there are two AVX workloads, BPP and SFT, where the P-core effective clock drops to 4.5 GHz. This is expected as the 5 GHz P-core frequency is reduced by 500 MHz due to the AVX offset. During the FFT workload, also AVX, the frequency is back to 5 GHz, so the AVX offset was not triggered. Then the next 4 AVX workloads, N64, HNT, VST, and C17, bounce back and forth between the AVX offset and non-offset. Advanced voltage offset was first introduced with the Comet Lake architecture in 2020 and is of course inherited by Alder Lake. It is more commonly known as the VF offset or the VF points. It is an extension of the adaptive voltage mode that we're all too familiar with. Advanced voltage offset exposes some of the points on the VF curve to the end user and allows for manual adjustment of these points. The amount of VF points is not architectural and can change between SKUs. In other words, specific CPU models can have more or less predefined VF points. The only requirement for the VF curve is monotonicity. Following a monotonic function, as a rule, the voltage for a given CPU ratio must be equal to or higher than the next lower ratio. So, the voltage for 48x must be equal to or higher than 47x. The main purpose of the advanced voltage offset is to provide end users with the ability to undervolt their CPUs at specific parts of the VF curve. In addition to undervolting, this feature also allows overvolting. This is particularly useful when manual overclocking and when you are trying to increase the maximum frequency. The advanced voltage offset function is commonly used in two ways. First, you configure a positive voltage offset for the highest VF point. This helps achieve higher single core overclocks. Second, you configure a negative voltage offset for the second highest VF point. This helps achieve lower voltage for an all-core overclock, which results in lower temperature in all-core workloads and thus potentially additional overclocking headroom. On Alder Lake, this approach is a bit trickier because of the available VF points. On the 12900K, the highest VF point is 53x and the second highest VF point is 48x. This lack of granularity will be a headache for anyone trying to balance a high single core and high all-core overclock. Next weird thing with Alder Lake is that the amount of available VF points has increased from 8 to 11. However, points 7 to 10 are all copies of VF point 11. This is by design, it's not a bug, but we don't know what it's for. Possibly for future products. Upon entering the BIOS, set the advanced mode and stay in the tweaker menu. Set enhanced multi-core performance to disabled. Enter the advanced CPU settings submenu. Set active turbo ratios to manual. Set turbo ratio for 1P core and 2P core active to 55. Set turbo ratio for 3P core active to 54. Set turbo ratio for P core active to 53. Set turbo ratio 5P core, 6P core, 7P core, and 8P core active to 52. Set turbo ratio 1E core to 8E core active to 40. Leave the advanced CPU settings submenu. Set extreme memory profile XMP to profile 3. Set vCore voltage mode to adaptive vCore. Set VF offset mode to selection. Set VF.6 offset to minus 0.025 volt. Set VF.11 offset to plus 0.075 volt. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. We achieved the best performance in all our benchmark applications. The highest performance gain is in AI benchmark, where we increased by 18%. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4918 MHz, and average CPU E-core clock is 3996 MHz with 1.197 volts. The average CPU temperature is 99 degrees Celsius, and the average CPU package power is 303.2 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5151 MHz, and average CPU E-core clock is 4000 MHz with 1.281 volts. The average CPU temperature is 99 degrees Celsius, and the average CPU package power is 311.8 watts. Before I jump to the conclusion, let's first have a debrief on overclocking the Core i9-12900K. First of all, there's genuinely a lot of overclocking headroom in the Alder Lake CPUs. While I didn't quite get it running stable for my manual overclock, the CPU was able to run at 5.6 GHz on multiple P-cores. And I've seen other 12900K CPUs that can even do 5.7 GHz on custom loop water cooling. That's really exciting. The main challenge you'll face when overclocking is the big range between the one core maximum frequency and the all core maximum frequency. To set a dynamic overclock, you need to use adaptive voltage mode and the advanced voltage offset. This allows you to set the target voltage for the one core maximum frequency, as well as keep a dynamic voltage scaling with the lower frequencies. For the 12900K, there are only two VF points relevant for manual overclocking. The highest VF point, which maps against our highest ratio, and the second highest VF point, which maps against the 48x ratio. In our manual overclock, we have a one-core maximum overclock of 5.5 GHz and an all-core overclock of 5.2 GHz. We can control the target voltage for 55x using the highest VF point. However, we have almost no control over the voltage of 52x. The lack of control is annoying, as it's really important to fine-tune the voltage in an all-core workload to manage the temperatures. Speaking of temperatures, as you can see from the Prime 95 results, even at default settings, there's not much thermal headroom to push the all-core frequency. When unlocking the Turbo Boost 2.0 limits, we already hit 100 degrees Celsius in an all-core AVX2 workload as the CPU package power hits 300 watts. The TJ Max, or maximum temperature, is a safeguard against any long-term damage as it throttles the CPU frequency to stay within the guaranteed operating temperature. Due to the new way Intel handles AVX ratio offset, it's still worth pursuing higher all-core frequency, as some light AVX workloads will not trigger the offset. In terms of voltage, it's important to note that they're much lower than what we're used to on previous Intel platforms. Whereas on Rocket Lake we'd see over 1.5 volt even at default, on Alder Lake the default voltage ranges up to 1.3 to 1.35 volt. In short, here is how I would approach P-core overclocking. Single P-core maximum voltage around or slightly higher than 1.4 volt, and expect 5.5 GHz to 5.7 GHz maximum frequency. All P-core max voltage around 1.2 volt if your cooling solution can handle it, and expect between 5 and 5.2 GHz maximum frequency. I would suggest to leave the E-cores at default as the performance impact is minimal and overclocking capability is limited to about 4.2 GHz. Alright, let's wrap this up. I had already tested an Alder Lake 12900K CPU prior to putting together this system, so I was primarily interested in confirming my initial overclocking results. Also, I was keen on figuring out how Gigabyte had approached this totally new architecture and totally new DDR5 memory. Overall, I'm pretty pleased with how my manual overclock turned out. I'm sure there was a little bit more performance in it if I was able to get my CPU stable to that 5.6 GHz. But then again, 5.5 GHz on all the P cores is nice as well. I think with Alder Lake, the traditional way of overclocking Intel CPUs, that is, just apply one ratio to all the cores and have it leave at that, is officially dead. To maximize the performance, you really need to set a dynamic overclock where many cores are going high, few cores are going even higher, and then you have one or two cores that go the highest. By default, the Z690 AORUS Master is very aggressively tuned, as it has the Turbo Boost 2.0 limits fully unleashed. That means that you'll need very good cooling to keep the 12900K within check in a AVX all-core very heavy workload. I was most impressed with the work that Gigabyte had put into the DDR5 aspect of Alder Lake overclocking. There are plenty of new memory tuning features, including the SPD setup, which open up a lot more tuning opportunities. It's still very early days for DDR5 overclocking, so it's kind of difficult to gauge to what extent the motherboards are meeting or even exceeding DDR5 overclocking expectations. Anyway, that's everything for today. I will definitely have more SkatterBencher Alder Lake overclocking guides up in the future. If you have any questions or comments, as per usual, feel free to drop them in the comment section below. And thanks for watching. See you next time.